I'm Patrick Folge from the group of Christine Silberhorn at Paderborn University, and today I will talk about our work on fully reconfigurable quantum state interference in a frequency encoding. So let me begin by showing you this very general picture of a linear optical quantum network, which is what we want to build in this work here. So this starts with some multimode quantum input state, which is sent into a multi-port interferometer, where the state is somehow processed and then detected in the end layer. And this kind of scheme is crucial, for example, for Gaussian boson sampling or measurement-based quantum computation schemes. But at the moment, scalability of these kind of systems is very challenging, since this requires adding more and more components, which leads to growingly complex setups, which are hard to stabilize, and so on. And because of this, we want to introduce in this talk a novel platform for the implementation of these schemes, which we believe might bring some benefits. And we want to show our first experimental implementation of the scheme. Okay, so the scheme we are envisioning is built in the frequency domain using frequency bins, which is nice since these are intrinsically high dimensional. It's compatible with existing fiber infrastructure. However, the question is then, how do you interfere different frequencies? And there are already some existing approaches. Many of them, like in this work here, use electro-optic modulators and sideband generation. There's multimode homodyne detection approaches, but we want here to focus on nonlinear frequency conversion processes to implement this interferometer. Okay, let me go very briefly now through the scheme which we are envisioning, and then I will go through the individual components in more detail later. But as I said, we want to build something which looks like this. So at the beginning of our source, of our scheme stands a type 0 PDC source, which generates the quantum input states. And we use a type 0 source because this generates strongly frequency correlated states, which provides us with input states in the frequency bin basis, which we are considering in one process. Then at the heart of our scheme is this so-called MQPG, which is a specifically designed frequency conversion process, which we use to implement the interferometer. And it can do this because it can map a set of input frequency bins to a set of output frequency bins. And the cool thing now is that we can, by changing the pump field, which drives this frequency conversion, change how this connection between input and output is happening. So by changing this, we can change what kind of interferometer we want to implement. And then in the end, we have to do spectral demultiplexing to separate all the frequency bins and to detect them. And in completeness, this thing is then completely analogous to the spatial encoding depicted above. Okay, let's go a little bit more into detail into the individual components. As I said, we start from a type 0 PDC source. This is characterized by its joint spectral amplitude, which shows how the signal and idler photons which are generated are correlated. And as you can see in our source, they are very strongly correlated, which results in the fact that this is a very multi-mode process, which actually here is not a problem, but a feature for us. And I want to highlight this degeneracy point of the source, which is the point where signal and idler are identical, because this is crucial for later. So if you now think about the source generating a broad spectrum, we find that if we now look in the frequency bin basis we are considering, that we find two-mode squeeze states in pairs of frequency bins which are shifted symmetrically around this degeneracy point. So we have in all these different pairs of frequency bins now two-mode squeezed states. And this is what we can use for our input state for the interferometer. But let's come to the interesting part, namely how now do we build the interferometer in the frequency domain. And as I said, we want to do this with a dispersion engineered sum frequency generation process. Dispersion engineering here means that if you look in this input-output relation, which describes how input frequencies are mapped to output frequencies, we have this vertical orientation of the phase matching on the output axis. And now conversion happens where the pump function corresponding to energy conservation is intersecting with this phase matching function. And as you can see, if we now use a pump which consists of two pump bins, we have two intersection points which now select two input frequency bins, but due to the orientation of the phase matching, both are superimposed in the same output channel, and this allows us to have this multipath interference necessary to build linear quantum networks. Now, to get multiple output channels, we employ employ superpolling strategies in our waveguides to split the phase matching apart to get access to multiple output channels, which we can then individually control with different pump regions. So we can control the amplitude and phases of these intersection points by shaping the pump. And then, for example, if we put now a minus phase on one of the bins here, this would be then analogous to the spatial beam splitter, basically, but here in the frequency domain. The question is then, how do we build larger networks with this? And for this, quick recap, if we have a multi-port interferometer, like this, we can describe its action by a unitary matrix view, which describes how input modes are mapped to output modes. And basically, it describes in one column how the input modes are superimposed in the output modes of the interferometer. So if we now come back to the transfer function of our process, now here realistically simulated, again with 2 output channels, but now with 6 bins per channel due to the pump shape, we can now directly take these entries from the unitary matrix and directly imprint them via pulse shaping onto our output channels. So we get exactly the same superpositions in these output channels here as we would get in these output channels of this linear network above. And due to the fact that we only have 2 output channels for now, it's equivalent of measuring in 2 different output channels of this network. But since we have full control over amplitudes and phases in these channels, it's basically fully reconfigurable and we can implement any kind of interferometer we want here. Okay, so how do we do that in the experiment now? We start, as I said, from our type 0 PDC source, which we pump with a pulsed laser at 775 nanometer to generate our squeeze light at telecom. This provides us with these squeeze states in the frequency bin basis, which we then send into our second nonlinear crystal in the MQPG, where we combine it now with a classical pump field, which comes from a second pulse laser at 860 nanometers now, which we then first send into the pulse shaper to carve out the frequency structure we need to realize the transfer function we want. And then we have to get conversion also to synchronize the 2 pulses in here. So temporally they overlap, which we realize with a repetition rate lock. And then we get conversion into these 2 output channels. We filter out everything besides this upconverted light in these 2 modes here. This we send into a spectral demultiplexing stage, which we build with filters for now, which then both modes go into 2 separate fibers, into 2 separate APDs. And now we can measure the coincidences and singles in these 2 channels. And then this kind of system here is completely analogous to this spatial network picture, where we have 3 2-mode squeezed vacuum states in the input of a fully programmable unitary, and we can measure at 2 output channels simultaneously. But we can scan through these different combinations here by reprogramming our transfer function via pulse shaping. And this is then exactly what we did in the experiment. So as a first test unitary matrix, we went to the DFT matrix, so the discrete Fourier transformation matrix, because this has a nice feature of having equal amplitudes. So the unitary matrix, all entries have the same amplitudes. So we, as you can see here, so we only have to shape now the phases according to this matrix. So we take now the columns here from the phase and print them on one channel here, and then this corresponds to one output channel. And if we do this and first simulate it, the normalized coincidence pattern we would expect looks something like this. Here you see what output channel of this matrix we imprint on this channel, and here you see what we imprint on here. And then we scan through all the different combinations. And when we do that the first time, okay, it doesn't work. Why? Because we had a lot of spectral phases in our system, and this basically adds another set of random phases which on this transfer function here, which messes up the phase relations. So we have to come up with a phase compensation algorithm, which scans every bin against each other bin to set all the phases relations properly. And if we do that, it works. Very cool. Problem this is a little bit boring because the coincidences which are on the off diagonal are all just equal, basically. So we wanted to see if we can see some more interesting patterns here. So we added in just a simple pi phase shift in one of the input channels. repeated the measurement, and it drastically changes the coincidence pattern we get now, and we still are able to see this. So I want to stress here that we have really good phase control here. So we up to the input squeezer rotation without any active phase stabilization or anything. This is all just in the process itself. So we went further, added another pi phase shift, and we still are able to recover this coincidence pattern. But now we wanted also to attack the final boss, let's say, going for full random unitary matrices. So we have basically to demonstrate that we have really full control over what interferometer we are implementing. So we chose some random matrix here. Note that this then also involves changing amplitudes and phases according to the entries of the unitary matrix on this transfer function, but this still works. So we could demonstrate that we really have full control over what kind of interferometer we want to implement in this network. And with this, I want to conclude. So first, I showed you the rough layout of the network scheme we are envisioning to build these kind of linear networks in the frequency domain, which has some benefits in our opinion, that it's first of all fully programmable just via pulse shaping. Note that this put a lot of the complexity of this implementation on the classical pump field, because other frequency domain approaches often rely on shaping also the quantum light, but a lot of the complexity here is addressed on the classical part basically. Only requires 2 nonlinear waveguides for implementation, and it's intrinsically phase stable. And then I showed to you that in our first experiments with this, we actually managed to implement fully control over the unitaries we are implementing with this. And the outlook is quite simple, going to higher dimensions, so adding more outputs and inputs. Thank you very much, and I'm open for questions.
Thank you. Thank you. Questions? Please.
Thank you for the nice talk. Maybe I missed the point, but you mentioned that in this experiment you did you used 2 APDs for the photon detections, but like you observed 2 modes out of the 6 initial modes by using some filtering, so to say. And is it also possible to do a simultaneous measurement onto each of the modes, or for example, like using the hormone detection together with some.
Do you mean if you can measure all channels simultaneously?
Yes.
Yeah, that's in principle possible. That's the problem here for us is what waveguide we are using basically here. So because let me go back. So what determines the number of output channels is basically splitting apart the phase matching function here into multiple output peaks. And this depends on what kind of superpoling structure we employ in our waveguide and into how many output channels we are splitting this. And for the sample we used for this work, we just used the splitting into 2 output channels. But there's published work from our group in this paper, for example, where we have MQPGs published with up to 5 output channels, and there's no reason to not be able to go further in principle with that. You will hit a limit at some point because these patterns become quite complex, but it is possible to add more output channels simultaneously with that scheme, yeah.
So in the beginning of the talk, you mentioned that one of the motivations here is to scale up the entire the optical structures. But what is the limitation you can reach? Like, is it also possible to scale up it into like hundreds or thousands of modes in these ways, or maybe?
There are some ideas with the platform we are using for now, which are standard periodically posed lithium niobate waveguides. I think that's very challenging. In principle, maybe, but not with the current platform. But there are other platforms we are thinking about where this might be an option. But that's very far in the future for sure.
I see. Thank you.
Thank you. Yeah, I will have a. No, then I don't have a question.
The source that you're using is highly entangled.
Yeah.
Do you do any filtering before sending it through the setup? Do you do any filtering or you just use the highly entangled state?
There is some filtering involved, but not to carve out these structures here, if you mean that. The filtering, this is something I didn't talk about in detail, is happening basically within the frequency conversion process, because it's a mode selective process. So it can only up convert the mode it's addressing. So it's actually only up converting this one frequency bins, and everything else it doesn't see basically.
I see.
So the filtering is happening in the process. Yeah.
And if you want to use like more of this, like kind of, okay, understand this can go to very high dimension, but if you want to include another source or another photon, then what would be the prospect there, like in terms of
another source or another network?
Like a completely different source, like if you want to interfere different like high dimensional frequency bins here, like what you would do?
I mean, this thing is actually just a linear interferometer for this frequency bin basis. As long as you can create states in the basis it's addressing, then it should just work fine still as a multiport interferometer.
Sure, but you cannot, like, if you have another source that, like, for sake of communication, for example, because the photons are highly entangled in source, then you wouldn't have very good interference between different sources, right?
So
I think we may need to move the discussion.
Okay, yeah, we can talk about afterwards
because it's growing.
Yeah.
Thank you.